linear contrast will allow us to test these more complex types of hypotheses. So what would be an example in which this type of hypothesis makes sense? Let's talk a little bit more about coffee as a motivating example. So in 2018, Angeloni and colleagues they published a paper where they looked at brew strength of coffee. So this is coffee strength we're looking at here. So their response variable was total dissolved solids. So you can just think of that as coffee strength. How much coffee sort of molecules do we have floating around in our water? And they were interested in brewing coffee at relatively cold temperatures. So their explanatory variables that they were interested in were different temperatures and their different methods of brewing. So they had these recipes, and there were 5 total recipes. So the factor was recipes, and the levels of the factor was, there were 5 of them, but they had the structure, which was related to the temperature and to the method of brewing. So let's go ahead and look at some of the data that they have here. So they have recipe 1, 2, 3, 4, and 5. And recipe 1 had the method of drip brewing. Drip brewing is where you take the coffee and you basically have a bed of grounds. So maybe like a funnel here, and you've got a bunch of coffee grounds all through here. And the idea is that the coffee drips down into your cup. So that's a drip method. They also had immersion method. If you're familiar with the French press, you'll know about an immersion method. So in the immersion method, you have a large container, and you put the coffee grounds in the bottom of the container, and then you fill that up with water, and these coffee grounds just sit immersed in the water. So we have recipe 1 was drip, and recipe 2 had immersion. Now they also varied the temperature at which they brewed. So normally coffee, if you drink coffee, it's normally brewed at quite close to boiling, but here they tested 2 cool temperatures. So one was quite cold, 5 degrees Celsius, and the other was 22 degrees Celsius. So recipe 1 and 2 were both at these 5 degrees. Recipe 3 and 4 were at these 22 degrees Celsius, about room temperature. And recipe 3 was also a drip method, and recipe 4 was an immersion method. So we haven't really covered it in depth yet in this class, but this drip method, the experimental design here is a 2 by 2 factorial. We have 2 factors, method and temperature, and each has 2 levels. Now this 5th recipe, though, is a little bit different. This is also immersion brewing, but the temperature was 98 degrees Celsius. And so this 5th recipe is kind of an odd man out. That's just a standard French press brew. So it's brewed at hot temperature, immersive. Now our response variable was total dissolved solids. Total dissolved solids, so that's coffee strength. And for recipe 1, this is the mean total dissolved solids for all of the samples brewed with this recipe. It was 14.023. For immersion, it was 18.421. Recipe and temperature 5. Recipe 2, method immersion and temperature 5. For recipe 3, the mean was 18.004. For recipe 4, the mean was 22.746. And for recipe 5, the mean was 27.351. Now we also need to get a sense of the variability here. And so the authors of this paper also provide the sample standard deviations. For recipe 1, the sample standard deviation was 3.434. For recipe 2, it was 0.686. For recipe 3, it was 4.765. Recipe 4, 0.687. Recipe 5, 3.711. All right, so looking at these data, we can see that there's some differences in the mean total dissolved solids. It also appears that there is quite a bit of a difference in the standard deviations from one recipe to the other, which might be problematic, but we'll address that later on. Now, it wasn't clear from this Angeloni paper what the sample size was for every recipe, but for here we're going to assume that n equals 3, so that there were 3 samples for every recipe. Now that you see that there's a sort of structure to our recipes, we can think about some comparisons of the recipes that might make sense. So for example, let's say that we wanted to test, is the mean total dissolved solids different between those recipes that are brewed at a temperature of 5 compared to those recipes that are brewed at a temperature of 22. So here we can think about writing our null hypothesis as the average is the average of mu1 and mu2 equal to the average of mu3 and mu4. And we'll do that right here. So our null hypothesis of interest is mu1 plus mu2 divided by 2, the average of these two, equal to mu3 plus mu4 divided by 2, the average of those. So basically do we get the same total dissolved solids when we brew at 5 degrees as we do when we brew at 22 degrees? Our alternative here would be the two-sided alternative that these averages are not equal to one another. Now, writing the null and alternative hypotheses like this is fine, but there's another way we can write it that will reveal the structure of the linear contrast. So we can think about moving all of these terms to the same side of the equation and then distributing this factor of a half to each of the mu's. So we can rewrite this as 1/2 times mu1 plus 1/2 times mu2 minus 1/2 times mu3 minus 1/2 times mu4 equals 0, versus the alternative hypothesis that 1/2 times mu1 plus 1/2 times mu2 minus 1/2 times mu3 minus 1/2 times mu4 is not equal to 0. Now these hypotheses are in the form of what we call a linear contrast. So a linear contrast we define like this. Suppose that we have a factor with A levels. So A is number of levels. In this case, we have 5 recipes, so we have 5 levels here. And there are means corresponding to each of these levels. We'll let C1, C2, all the way up to CA, C sub A, denote what we'll call contrast coefficients, such that the sum of these contrast coefficients from I equals 1 to A is equal to 0. So the constraint on these contrasts is that they add up to 0. Then we can define a contrast like this. We say that gamma, this contrast, is equal to the sum from I equals 1 to A of each contrast coefficient, C sub I, times the mean for that level, mu sub I. So in other words, this is C1 times mu1 plus C2 times mu2, and so on, all the way up to CA times mu sub A. Looking at the example above, we can see that the contrast coefficients are, we have C1 equals 1/2, that's right here. We have C2 equals 1/2. We have C3 equals negative 1/2. And we have C4 also equals negative 1/2. Now, not shown up above there is also our C5, the fifth contrast coefficient. We have 5 means in our case here, and the fifth contrast coefficient is 0. And that's why we have no mu sub 5 here, because that's not a part of our hypothesis of interest. So its coefficient is 0. Also note that these contrast coefficients sum to 0, and so they're valid contrast coefficients. 1/2 plus 1/2 minus 1/2 minus 1/2, that gives us 0.